Was his brain responsible for his predator prowess? Finding this answer will be a challenge because bones fossilize, brains don't. So how do we prove it? It's taken 65 million years, but at last we have the technology to look inside the bones for clues. Paleontologists have dug up only a handful of skeletons that are greater than 50% complete. Often the bones of the skull, if found at all, are scattered or crushed. But there is a T-Rex named Stan. He has an immaculate skull and is Phil's best chance to reconstruct the brain of T-Rex.
I've always wondered whether it would be the sight, hearing, or smell of this animal that would have hunted me down and nailed me. Because it is seen as the ultimate predator. But was it? Was it some lumbering animal that sort of staggered into its prey just by luck? Or was it a calculating killer? If we're going to get that answer, it's going to be from inside of there.
Buried right behind the eyes is the brain case. The brain case is empty because the squishy brain doesn't fossilize, but the interior contours mimic the rough shape of the brain it once held. And the shape of the brain gives clues to how Stan responded to his world, how well he could see, smell, and hear. To solve this case, Phil will need to pull out all the stops to borrow Stan for some tests. While on the hunt to see if the T-Rex's brain helped make him a super predator, paleontologist Phil Manning gets a very special delivery. It's the real deal, the actual fossilized, intact brain case of Stan the T-Rex.
Every once in a while you get to play with something really special. There's only one like this in the whole world, and just to touch it, it's goosebumps. It's amazing.
Phil spent years negotiating access to this 65-million-year-old fossil. Now he's about to become the first person to get a look inside. He brings the ancient brain case to Nikon Metrology in London. There he'll have access to the company's highly powerful CT scanner.
I think it's about time we gave Stan a suntan.
As Andrew Ramsey performs a preliminary scan, the device fires a super high-energy beam. It's an intense moment for Phil as the results begin to filter in.
The detail is incredible. That has the potential for the first time to allow us to peer inside Stan's brain, or certainly his brain case.
That's great.
That is stunning. I can't wait to see the CT scans.
So let's see how we get on over the next few weeks then.
Weeks.
Afraid so.
It'll take weeks to receive the in-depth results, which gives Phil time to investigate the latest research on the senses of T-Rex. It's critical for Phil to decipher how Stan used his eyes, ears, and nose, because each sense influences the shape of his brain. Since Stan's skull had enormous eye sockets, Phil starts by taking a look at his vision. Kent Stevens at the University of Oregon applies his expertise in computer science to his fascination for dinosaur mechanics.
The big thing about the T-Rex is everything that could get in the way is pushed out of the way. If you take a look, first of all, looking straight down its snout, it's like the raptorial birds.
The scalloped edges of the snout give T-Rex an unobscured view when looking straight ahead. Kent's computer model demonstrates why two eyes are better than one. The cones illustrate the concept of field of view. Where they intersect, that's binocular vision, the same as humans have, and essential for T-Rex to estimate the distance to its prey. T-Rex also has wide peripheral vision. While it draws a bead on its prey, it can keep a lookout for rivals moving in from the sides.
That is remarkable. So really, these visualization tools that you can generate can help understand more than just sort of vision. It can help interpret fossils. That is really powerful tool.
It's confirmed T-Rex had killer eyes. But what about his sense of hearing? For this, we look to the alligators in the swamps around the Kennedy Space Center. They share a trait with rockets and T-Rex. They all produce the deep bass notes called infrasound.
Aerodynamic pressure.
Roaring at over 200 decibels, rockets like the space shuttle make one of the loudest human-made noises on the planet.
Standing by. Throttle down.
As the low-frequency sound waves roll across the swamp, they don't go unanswered. Male alligators think it's a rival male threatening their turf, and they're ready to rumble with infrasonic roars of their own. Our ears can't detect the ultra-low frequencies, but we can see how the sound makes water dance on their back. Inside T-Rex's skull, a series of large air chambers connected to the middle ear increases sensitivity to the infrasonic rumbles. It seems T-Rex had sophisticated hearing and exceptional vision. But what about his sense of smell? When scientists need their heads examined, they go to see Larry Whitmer in his lab at Ohio University, and more like a bloodhound. A human's nose has about 6 million scent detector cells. A bloodhound has around 300 million. And T-Rex, with its enormous snout, had room for many more than that. When it comes to the sense of smell, it seems T-Rex was the winner by a nose. But Phil won't know for sure until Andrew Ramsey finishes Stan's brain case scan, still spinning under the interrogating rays of the CT scanner. Even without those results, Phil's made astounding progress. He has determined that T-Rex had the potential for sharp vision, hearing, and smell. But once all that sensory information entered Stan's brain, did he have the smarts to use it to his advantage?
I'm starting to suspect that the Tyrant Lizard King may have been a lot more sensory savvy than we've given him credit for.
Back in London, the scan is complete.
We're literally the first people ever to stare inside Stan's brain case.
right.
Look at that. That's the olfactory lobe, sort of the front, the sensory part of the animal, all to do with smell. They are huge.
Stan's brilliant brain case confirms what Phil deduced, right down to the supersized olfactory lobes. Stan's smell center practically dwarfs the whole hind brain.
If the size of these bulbs correlates to sense of smell,
Yeah.
this thing had amazing sense of smell. Clearly a predator.
Using its infrasonic hearing, wide peripheral vision, and super sensitive sense of smell, there's no doubt that T-Rex was a ferocious, calculating killer, and he used his super powerful brain to process all that sensory input. The rest is prehistory. In the kill or be killed world of the predator, dinosaurs suffered colossal injuries that would kill most predators today, and limped through a land rife with deadly infection and disease. Yet they were some of the most successful animals ever. How did they do that? Paleontologist Phil Manning is gung-ho to discover what made dinosaurs such tough survivors.
A dinosaur's speedy recovery meant it was less vulnerable to large predators or starvation. But I'm thinking about the most insidious killer of all, infection. We don't see much of it in the dinosaur world, and I want to know why.
Now here's a dinosaur that really knew how to survive. It's Gorgosaur, a type of tyrannosaur, and its fossil was found with a horrific injury. Its right leg is smashed to pieces, believed to be the worst compound fracture ever found in the dinosaur fossil record. This Gorgosaurus should have died from its injuries, but didn't. Phil is at Purdue University School of Veterinary Medicine in Indiana with veterinary pathologist Kevin Donnelly to learn more about these kind of injuries.
So, compound fractures? Sure, and I brought something for you, Phil.
I don't know whether I should be more worried that you have a stocking in your pocket
Or what do you expect me to do with it?
Well, let's use this to emulate skin. So I think if we put this on the bone, we'll be able to demonstrate what an open fracture looks like.
Phil tries to smash a broad area of a horse bone and break it into pieces like the leg of Gorgosaurus.
Hopefully I hit it square.
The blow strikes across a wide area, producing fractures in all directions.
That would really hurt.
Yeah, that bone shattered very nicely.
Oh, ugh, that is grim.
So there's a shard of bone sticking right through as if it was poking through the skin.
It would have been a devastating blow to Gorgosaurus's leg and make the job of knitting the bone together much tougher. With a shattered leg, Gorgosaurus would be in a tough position to pursue prey.
That's going to cause huge problems because, of course, skin is this wonderful barrier between the environment and the innards of the animal.
When the infection sets up in here, it's going to prevent these bones from healing properly, and it also has serious consequences for the systemic infection in the entire animal's body. It's the kind of fracture that usually results in death.
But somehow, it is the infection that stops dead in its tracks. The Gorgosaurus survived to fight another day. Phil suspects it wasn't just luck. He believes the Gorgosaurus's immune system was exceptionally high-powered. It's a trait that dinosaurs share with one of their later cousins, the alligator. To get a better idea of how a dinosaur's immune system worked, Phil heads to an alligator farm to examine some gators. There he meets up with a severely injured patient. One of its back legs was bitten off, and the other leg has a nasty-looking open wound. The wounds need attention. But incredibly, neither leg is infected. Remarkable because a bite from one of these creatures is like waging bacterial warfare. Biochemist Mark Merchant seldom sees truly life-threatening infection in these animals.
While growing up in southeast Texas, I was around gators my entire life. I did a lot of fishing and hunting in areas where there were a lot of gators, and I noticed that they would be missing limbs often, but they heal very rapidly, and in fact, without infection, typically.
The best way to study a gator's immune properties is to get blood from it, live.
No, you're okay. You're okay. Most of the immune system components are in the blood.
And to extract this information each time, you have to do this.
Yeah, it's...
You're insane, man.
This is the fun part of the job.
The fun part? Oh, man.
Mark manages to coax some gator blood without shedding a drop of his own, at least until now.
I'm going to draw a little bit of my own blood. I use this as normal human serum, which is a bit problematic, if you consider me normal. But
I'm not going to answer that one. I've just seen you riding a gator. There's nothing normal about riding a gator.
So I can draw just a little tube of human serum here, and we'll compare that.
Once Mark collects gator and human blood samples, he isolates the part of the blood that contains the infection fighters. He'll test the two samples to see if gator blood delivers a bigger bite against disease.
So you're literally separating out the different building blocks of blood?
That's correct. We're going to separate the cells, the red and white blood cells, away from the clear part, the liquid part that we call plasma.
After the blood spins at high speed in a centrifuge, the lighter plasma containing the infection fighters rises to the top.
I'm putting gloves on for this, especially because we're dealing with your blood. Who knows what's inside your blood?
The yellowish plasma contains proteins and infection-fighting agents. There's more plasma in the gator's blood on the left than in Mark's on the right. Mark prepares a batch of nasty bacteria called MRSA, a strain that notoriously resists antibiotics.
What I want to do now is I want to take this mixture and put it onto this petri dish.
He spreads the bacteria over a nourishing growth medium where it will flourish overnight.
If you plate the bacteria, spread the bacteria without adding any serum, here's what you see. Look at all the bacteria. There's probably maybe 500 or 600 bacterial colonies, and each one of that represents a single bacterium.
Mark combines the human serum with the bacteria. After the mixture sits overnight, it's clear that the human infection fighters hardly made a dent in the number of bacteria.
by the same token, if we spread the bacteria that has been mixed with the alligator serum and let it incubate overnight, you can see that the alligator serum has really, really reduced the number of bacteria greatly.
It's actually wiped it out.
That alligator serum probably killed roughly 95 to 98% of the original bacteria that it encountered.
Crocs pack a powerful immune system. Their infection fighters are primed to defend against bacterial invaders the first time it meets them, while the human immune system works best after infection. Mark's work suggests crocodilians didn't acquire that system recently. It may reach as far back as the gators and dinosaurs' common ancestor.
What we're seeing here is a very ancient molecular innate immune mechanism. It goes way back to the early days of crocodilians and dinosaurs, several 100 million years ago.
His investigation suggests that never before has a group of animals been so close to indestructible. With a super immune system, the Gorgosaurus could keep deadly infection at bay in its mangled lower leg. It bought the animal critical time to repair its wounds and stay in the race for survival. From their healing powers to their speed, dinosaurs had a range of exceptional abilities. Take locomotion, for example. Believe it or not, some strange fossils are leading scientists to wonder, could some of them have hopped like rabbits? Phil's heard of one type of dinosaur whose fossil indicates that it could hop, and he heads to Swarthmore College in Pennsylvania to investigate. Poposaurus is a basal archosaur, a member of the ancient group that also includes crocodiles, dinosaurs, and birds. 200 million years ago, while dinosaurs evolved, basal archosaurs ruled the world. It's believed the Poposaur, the only one of its kind yet discovered, has a skeletal structure unlike anything that came after it. Poposaurus had tiny arms with 5 delicate fingers, large hip sockets and thigh bones, and especially large ankle bones. Did it walk on 4 legs like crocodiles? 2 legs like some dinosaurs? Or something else? The Poposaur isn't talking. It's up to Phil and paleontologist Emma Schochner to unravel the mystery.
You really do have a fabulous beastie here. I can't get over how odd it is.
It's Freakosaurus. It shouldn't be called Poposaurus.
Freakosaurus. The weird thing about this animal is how the thigh bone went into the hip socket. So in dinosaurs, the thigh bone kind of goes in at an angle, but this animal, it went into the hip socket directly from below, like this. So it changes completely how the animal moved. It makes everything different.
I think if you're going to really work out something about the locomotion of this animal, the only way you're going to do it is by literally squeezing the whole animal into a supercomputer and saying, how do you work? Come on, just look at it. Do a very unscientific thing. What do you reckon it's going to come out like?
With a heel bone like this, elongated feet like that, I would love to say it hopped. I'm hoping the computer spits out something like that. We're gonna have to test it.
Paleontologists Phil Manning and Emma Schochner are investigating the unique movement of one of the earliest dinosaurs, the Poposaurus. The question is, could this creature hop? To find out, they start by creating a digital record of the skeleton. What looks like a supermarket barcode reader is a state-of-the-art laser scanner.
So whenever I point this laser now at this object, do you see on the screen, see the red laser? That line represents exactly what we're scanning onto the bone.
Scars on the bones indicate where the major muscles attached, but don't indicate their size. Phil and Emma want to dissect 2 modern animals related to the Poposaur, a gator and an emu. With its long tail and powerful legs, the Poposaur superficially resembles both. But how did the parts fit together on the inside?
I'm just grateful I've got the easy one to handle. Having problems there? Hang on. Ah, that's gross. You hit me in the face with a dead emu. Okay, let's peel back and see what we can see in terms of leg muscles on the emu. Oh, that's beautiful.
Look at these calf muscles. Look at this.
Well, it's clearly one that's very important for the locomotion of this animal. It's fantastic. You can see the tendons there, how useful they are at flexing and extending the foot. So useful for being a fast runner.
Scars on the Poposaur's leg bones suggest that its muscles and tendons resembled the emu's and attached in a similar way. But the emu doesn't have giant ankle bones like the Poposaur does. There's more shrouding the answer to how the Poposaur moved. Its tail, broad and muscular like a gator's, no doubt played a big role in the Poposaur's locomotion.
Thing is, flip this beastie over, then we can have a better look at these muscles. So, do you want to turn that way?
Yep. Let's swing him around.
Sorry, Mr. Gator. There we go.
Hold back these tail muscles.
Wow, that's fantastic. Look at the size of that muscle.
Especially after cutting up the emu. I mean, this muscle it's huge. I mean, this primarily pulls back the thigh.
Well, it's quite clear that having a muscle this big, it's involved in locomotion, but you've got two things going on here. Clearly, the leg is one, but this great big thick tail, a wonderful bit of locomotory sort of energy can be delivered by this muscle.
The dissection suggests that the Poposaur bears more than a superficial resemblance to an emu and gator. But how it all comes together with the unusual hips and ankles is something for computational zoologist Bill Sellers to decide. Bill has developed GateSim, a software that takes a virtual skeleton and attaches muscles to determine the movement of animals. Using the digital bone scan, Bill has created a virtual Poposaurus skeleton. He attaches the red virtual muscles to the Poposaur's lower half and lets GateSim get to work. The software makes hundreds of millions of calculations and finally reveals the motion of the Poposaur.
It's like a punk rocker pogo dancer at a concert. It was a punkosaurus, let alone Poposaurus or Poposaurus.
The software indicates that the Poposaurus may have hopped.
I mean, it can do it,
yeah,
but it's not high speed.
So hopping is possible, but not likely to be its usual gait.
But can the Poposaurus run?
That's fantastic.
And that's a bit more like it.
It is. That's stable.
Yeah, and look, in a second, it's already at 4 meters.
So that's quite respectable.
And actually, it's going a bit better than that now. So what's it going to do? 2 seconds and it's done 9 meters. At 4.5 meters per second. That's much more reasonable.
That's pretty good.
GateSim demonstrates that the Poposaur walked, ran, and hopped on 2 legs. So we finally answered our original question. Some dinosaurs could in fact hop. With unexpected traits like hopping, the Jurassic world was a place filled with strange wonders. One of the strangest was the sheer size of these dinosaurs. The largest ever discovered was a sauropod that was nearly 100 feet long and 18 times heavier than an elephant. So it begs the question, with a neck that spanned nearly 50 feet, how in the world did a dinosaur lift such a long neck? Munching their way through primordial forests, long-necked sauropod dinosaurs became the most massive land animals ever. No one's sure why its neck grew so long. One theory suggests sauropods used their neck to conserve energy by reaching a large feeding area without walking. But how could they raise such long necks? To find out, Phil heads to China to look at the world's longest-necked dinos. He meets up with veterinary anatomist Peter Dodson and paleontologist Hai-Lu Yu.
Hi, Peter. Oh, hi, Lou. Nice to meet you.
Hai-Lu has a sixth sense about dinosaurs. He's named 12 new species in the last 7 years. 150 million years ago, a sauropod named Dashier Titan was alive and well, grazing on green plants. At 50 feet, Dashier Titan's neck stretched longer than an adult T-Rex. Hai-Lu co-discovered it in 2008. In order for Phil to examine the necks, Hai-Lu's team offers to put the pieces back together and recreate the entire skeleton for him to study.
Please don't fall. This is like the ultimate health and safety video. Moving a scaffolding with 2 people on top.
The trickiest part is reassembling the neck. Dashier Titan has 19 neck bones, and they're enormous. Moving a neck like this would have required huge muscle power. And huge muscles are heavy.
Each neck bone has a rib on either side. These must have been part of the solution for growing really long necks.
The ribs not only provide structural support, they also give the large muscles a place to attach. The ribs at the base of the neck enable most of the heavy lifting. And some of these ribs grew taller than a man. But that poses another mystery. If super long-necked dinosaurs held their heads this high, they'd need a heart the weight of 2 small cars. If we assume that the blood has to flow uphill all the way, it would require more energy than it takes to fuel the rest of its body. But what if our assumptions about the angle of sauropods' necks are wrong? Paleontologist Phil Manning is on the hunt to see how the world's biggest dinosaurs lifted their massive 50-foot-long necks. He's learned that giant neck ribs allowed them to support the weight, and now wants to understand how blood could travel up to their brain. When it comes to reconstructing dinosaurs, paleontology is as much art as science. And when a dinosaur strikes a pose in a museum, there's no guarantee it's correct. Ken Stevens of the University of Oregon has written software that helps take the human element out of dinosaur reconstruction.
Going into museums, they change. They change the position of the skeletons, and I'm sat there with holding a plastic dinosaur that looks incorrect. What's going on with this?
Kent's Dinomorph software lets him reconstruct thousands of virtual dinosaurs and test how they moved. Impossible to do with actual fossils.
If you look at how the sauropods' bones fit together, they don't show any hidden curvature. They seem to be boringly straightforward, just moving from one bone to another. You're just following a smooth arc.
Kent's Dinomorph software has helped reveal that sauropods did not hold their necks upright. They held them horizontally.
If you simply make this kind of straight here, because there's absolutely no evidence to suggest that it went up.
Kent Stevens' work challenges assumptions and aids in redrawing the shape of sauropods. And it brings Phil to a realization. If sauropods didn't hold their heads way above their hearts, they would not need such high blood pressure. But the sauropods' neck ribs can't be the only reason they can manage the mammoth weight of a horizontally outstretched neck. There must be something else. Professor Matt Weddle might have the answer. At Brigham Young University in Utah, he's amassed a huge collection of hard data about bones.
This is a cathedral to ancient time.
Out of the thousands of bones in these catacombs, Phil's after just one. But it's a whopper, a Supersaurus backbone.
Blimey! That is huge!
One of the biggest vertebrae backbones of anything that ever lived.
But somehow, giant dinosaurs found a way to lug their big bones around. And the answer lies hidden inside the bones themselves.
Do you think the patient's going to survive, Doctor?
It's not looking good. I think we're going to have to amputate.
Matt and Phil slice into the leg bone of a cow to understand what makes mammal bones so heavy.
Yep. Oh.
Suddenly I'm not feeling hungry.
Now you can see that thick white bone around the outside, and the marrow inside is mostly fat, but with lots of blood vessels as well.
Modern animals build only as much bone as they need to support themselves, and normally fill up the empty space with marrow.
Oh gosh, look at that blood coming out.
Marrow is incredibly light and keeps mammal bones from getting too heavy.
It smells disgusting.
Yeah, look at that nice fatty marrow coming out. It's nutritious, but it's also just about the lightest, cheapest thing that your body can build to fill that space.
dinosaur leg bones had marrow too. No shocker there. But when Matt puts sauropod backbones through a CT scanner, he finds a real surprise. The X-ray slices from the CT scans revealed not marrow, but a honeycomb pattern inside the dinosaur's back and neck bones, filled only with air. Matt's work shows that the bigger dinosaurs got, the more air they had in their vertebrae.
This is one neck vertebra from Supersaurus.
A neck bone like this would have been light enough for one man to lift. The same size mammal bone would require a forklift.
Now, we found that the biggest of these sauropods, the vertebrae were about 90% air. So that's comparable to styrofoam.
So the bigger the dinosaurs got, the more air sac-like structures running into the bone.
Absolutely. They had found a solution that no other big animal has ever used.
So it's official, the biggest dinosaurs ever to have walked on the planet were potentially airheads.
Yes, they were airheads.
This feather-light adaptation is definitely a secret to sauropod success. And that, coupled with neck ribs and the realization that they held their necks horizontally, tells us how they held their ultra-long necks. For our next CSI mystery, let's take on Tyrannosaurus Rex. It was long ago determined that T-Rex could kick some Cretaceous butt. He certainly had powerful weapons. We've already uncovered so much about dinosaurs by studying their bones. But what could bones reveal about a dinosaur's appearance? For our final question, Phil turns his attention to unlocking the mystery of prehistoric color. Whether you're predator or prey, sneaking around, or strutting your stuff, you live and die by color. But nobody knows for sure how dinosaurs really looked. Paleontologist Phil Manning wants to use technology to help him crack the chemical color code to see if dinosaurs existed in living color. For this mystery, Phil will be using a machine called a synchrotron. It sees in a bold new light, firing highly focused beams 1,000,000 times stronger than a chest X-ray. But before he can use this state-of-the-art technology, Phil's got to get his hands on the perfect specimen to test. Bavaria, Germany. Ground zero for one of paleontology's great turning points. It's here in 1861 that a quarry worker discovers Archaeopteryx, half bird, half dinosaur. Just 2 years after Darwin publishes his Origin of Species, this magpie-sized bird with teeth, this dinosaur with wings, provides the first hard evidence that some dinosaurs evolved into birds. Scientists have pored over the Archaeopteryx fossil for 150 years. But Phil's team will be the first to study its chemical composition and look for hints of color.
Pete.
Hello, hello.
Good to see you.
It's one of only 10 specimens ever found. Escorted to the synchrotron lab by paleontologist Pete Larson.
Is that it?
That's it.
No, you're joking.
Little box. This is, yeah.
I can't believe that 150 million years in the making. It's probably the most iconic fossil on the planet. And you're carrying it in the back of your car like that.
We were disguised, you see.
Okay, that makes it okay. All right, let's get it inside. That's amazing.
The bones and some of the feathers of Archaeopteryx fossilized beautifully, but what became of the soft parts? The chemicals that once made up the flesh and feathers of Archaeopteryx, and colour, what became of that?
Based on the way Archaeopteryx fossilized, Phil's confident some of it's still there. That's where the synchrotron comes in. The synchrotron at Stanford's National Accelerator Laboratory is one of the world's most precise imaging machines. On its 755-foot-long track, magnets propel electrons at nearly the speed of light to explore subatomic particles. And now, Phil will try putting dinosaur color under its searchlight. If they use it to find color chemicals in the Archaeopteryx fossil, the team will have pulled off more than they ever dreamed possible. And Archaeopteryx will touch off yet another scientific revolution. The odds that any pigment chemicals survived 150 million years are extremely low. But Phil and his team accept those odds. The fossil's extraordinary condition is a good sign. No one has varnished or treated the stone with harmful preservatives. But there's no guarantee that there's anything left for the synchrotron to find. Now, after seemingly endless measuring and testing, the team's ready to start the scan.
We're going to interlock now. This is an interlock system.
Finding color is a shot in the dark. So first they set the synchrotron to search for one of the most common chemicals in the body, phosphorus. If the scanned image illuminates the fossilized bones, it'll prove there's a chance of finding something even more elusive. The chemicals of color. The scan begins revealing Archaeopteryx as no one has ever seen it before.
You have tremendous detail. You can see all the detail in the teeth, and then you can see these details.
You can actually see the elemental signature of the feather. Absolutely gobsmacking. That is amazing. The fact you can see the spacing in between the individual feathers as well, it looks like there's not been that much movement. It wasn't completely pulled apart when the animal rested at the bottom of that lagoon.
These aren't just enhanced views of the Archaeopteryx fossil. They're the actual X-ray image of phosphorus shown in bones and feathers.
The initial work we've been doing has shown us clearly we can see the structure and maybe even the original composition of some of the feathers.
The synchrotron proves for the first time that these fossil feathers left phosphorus behind. But further scans on the Archaeopteryx give only a hint of the chemicals that might suggest color, not enough to work with. Finding any colors hidden in this fossil appears to be a dead end. But Phil's got a lead on another fossil that may unlock the secret of dinosaur color. Paleontologist Phil Manning is in Liaoning, China, trying to answer the question, what color were dinosaurs? In the 1990s, this farming community became a boomtown for paleo prospectors, thanks to one man's lucky strike. In 1994, the farmer splits a slab of rock and makes history. The stone reveals the complete skeleton of a dinosaur, about the size of a turkey and covered in feathers. Since that discovery, fossil hunters have flocked here, scoring a bounty of feathered dinosaur fossils. Phil visits the office of paleontologist Hailu Yu to get a closer look at one of them.
Wow, I love your office. So what are you working on at the moment, Hailu?
I'm working on Ganser's food.
No spring chicken, the 110 million year old Gansus holds the record as one of the oldest known modern birds.
And I can see the foot hiding beneath the sediment there.
Still
That's stunning.
This duck-like bird lived at the time of the dinosaurs.
I'll show you another one. Have a look.
Oh, that is drop-dead gorgeous. Literally drop-dead in this one's case. It's as if though you killed this bird yesterday and squished it into the rock. You see, what I'm really after are the feathers. That's what I've come to find. Locked within the composition of each of these feathers is a color signature. And that is what we're after. And I think if we can work out from looking at these modern feathers where the color is locked into this protein, then imagine unlocking color in the fossil record. That for me would be so special.
You are lucky. I'll show you something. Look at this one.
Oh, that's beautiful. I've come an awful long way to look at a feather. Yeah, you can see there's variation in the tone of the fossil. Imagine if that is actual color. And I think the only way we can test that is by combining the information we learn from living feathers with the equipment that we can really subject this fossil to.
Now it's yours.
Thank you. I will look after them so much.
Next, Phil and the synchrotron team turn their attention to the Ganse's feather from China. It's younger than the Archaeopteryx feathers and may have a better chance of holding the secret ingredients of color if they can only figure out what chemicals to look for. Phil suspects those chemicals in the Ganses are from a pigment, so he also requests that they test some modern feathers. When they review the results, it appears the finely tuned X-rays confirm the presence of copper-rich pigment in both.
And what they're showing you is the distribution of these different elements in the feather. So you can see, this is the copper in the Turaco feather.
Ganses passed the test with flying colors. Phil can safely speculate we're looking at organic fossil pigments for the first time ever.
For me, unlocking the colour of extinct organisms has always been one of these goals that I thought we'd never achieve. But here I'm sat talking to you about unlocking the palette of colour in extinct animals.
Against the odds, technology helps Phil prove that within the fossil is the chemical ghost of the actual creature that perished there millions of years ago. In the future, the synchrotron may finally help unlock the complete chemistry of the prehistoric color palette.